And I want to tell you a story which actually started from Peter's email that he sent me in December about a very interesting article published by ScyllaDB guys who analyzed huge data set with 500 billion rows on some beefy cluster, and they got some very interesting performance results. Actually, the article was very good, and the results are interesting, but for us, for ClickHouse folks, it was kind of strange that for such a huge data set, for such a relatively small data set, they used a huge cluster. So I decided to play a bit with the hardware that I have in-house and try to do something similar on a single host. And I will tell you how it went. So let me introduce the problem a bit. So the problem that we consider here is Internet of Things. When we have, say, 1 million temperature sensors, probably in some homes, households, or just at streets, and they collect temperature data every minute and keep data for at least a year. This amount of data results in 1.4 billion measurements per day, or if you take the full year, it's 500 billion measurements, or 500 billion events. And the goal of the experiment is first to report on every sensor. We should be able to get the data for every particular sensor. Also, we need to be able to quickly detect broken sensors across all the farm. And it would be interesting also to build some temperature maps across all sensors and do some visualization maybe. So how much hardware is required for that? ScyllaDB guys, they kind of think that the beefy cluster is a good solution, and they used a cluster which had almost 3,000 CPU cores, 32 terabytes of RAM, and tremendous storage on solid state. This is all good and interesting, but with ClickHouse, we can actually do almost the same with very different hardware. So I took my Intel NUC, which we often use at conferences for some demos. It has only 4 cores and 32 gigabytes of RAM and 1 terabyte of pretty good storage. But the most unique thing about this Intel NUC is that it's powered by ClickHouse, which is an analytical database. If you're new to ClickHouse, these are main features. It's column store from ground up, so it keeps data in columns. It's optimized bottom up in C++, so it has a lot of low-level optimization, CMD optimizations for modern CPUs, vectorization, and stuff like that. It's SQL database, so if you know SQL, if you know MySQL, then there is no problem to write queries for ClickHouse. It's very portable, almost like MySQL. You can run it on a laptop, on Intel NUC, in cloud, or everywhere. It's scalable, both vertically and horizontally. So you can build clusters, or you can set up big machines. And it's certainly open source by Apache 2.0 license. And last but not least, it's very fast. Originally, it has been developed by Yandex, but it's currently it's still being contributed by Yandex a lot. But as you can see, there is a separate domain, and it's moving as a community project quite a lot. So what are main challenges when we're trying to solve this huge data problem? First, we need to manage volumes. Because if we do a math, and then in order to keep all this amount of data, we have to have several terabytes of storage, but on Intel NUC we only have 1 terabyte, and we need some space for operational system, for some other stuff. So in reality, we only have 700 or 800 gigabytes of storage, and we need to store data feed data in the storage. Then we certainly want to have a good query performance, and this is our goal. And we want to do it on a single mini PC. So rule number one, when you approach such kind of problems, is to know your data. You need to understand what kind of data you want to store, how it's organized, and how you can store it in the most efficient way. So in this particular case, if we are talking about temperature sensors, the data first is time ordered because we measure every minute, and every minute we have a new value. Second, the temperature actually changes smoothly. So every new measurement, it shouldn't be far apart from the previous one. So you can see it on a graph that it is continuous changes, right? Also, we may think that during the day there is some oscillation and there is some seasonal changes, etc. And all sensors are also different because they are set up in different places, and those different places also has different temperature profiles. But probably the most important is that the data is time ordered, so we have time series, and the changes are smooth. We can use it in order to make an efficient schema. And this is what our table looks like. Note several important things. First, we have encodings that we use in order to store data in most compact and efficient way. We have double delta encoding and a T64 encoding coupled with LZ4 compression. And I will explain in a minute what it means internally. Also, I used alias column here in order to extract date. And alias, it doesn't store data at all. So it's just an expression that can be evaluated by ClickHouse very efficiently. And last but not least is our ordering. We order data by sensor ID and time. And order in ClickHouse is very, very important. This is how the data is physically sorted on the disk, on the storage. And this is also a hook to ClickHouse primary key. So when ClickHouse queries the data, it uses both the primary key, which is a sparse index, and it relies on physical order on the disk. Once we have the schema, this is our rule number 2. We need to reduce I/O by all means. And this is where encodings help a lot. For example, what delta encoding does, it tries to encode deltas of deltas. This is why it's called the double delta. If we have the sequence of events, a sequence of some numbers like 5, 10, 15, 20, or 25 in this example, we can calculate the delta, which is 5 for all those events. And double delta is just 0. And if we are going to encode it in most efficient way, we can only use 1 bit per value, 1 bit per measurement. On top of that, since we have all bits quite the same, for this particular example, it might be different for different data distribution, it also can be very efficient, compressed afterwards using LZ4. As you remember, we use double delta for time dimension and for sensor ID, and we have ordering by time and sensor ID as well. That means that we have a very good data for double delta encoding. So it should compress very efficiently. T64 codec is kind of unique. It doesn't exist in other databases at all. It has been inspired by some academic article and implemented by Yandex folks. The idea is that if we have the data that doesn't use the full data type, then we can do a matrix transposition and convert it to the form that it's very easy to compress. So here on the left side, we have 8 words of data. Every word is 8 bytes. And we only change the minor byte, right? So every word is different, so it's kind of hard to compress efficiently. But when we transpose the matrix, we have a lot of zeros, which are just consecutive bytes, and one meaningful byte at the very end. So it can be very efficiently compressed. It works well for the data which is slowly changing, and this is unique for ClickHouse. Next, we need to generate the data. I don't want you to dig into logic of this fancy SQL script, but it generates the distribution with oscillations. You can see several sinus functions in there. And what we also do, we inject an outage, which is exactly the same outage that CLDB guys had in the article for particular sensor ID and time period. This is outage, and we will be detecting it later using our data. If you run this query, then you will have to wait. Yes, it takes time to insert the data. In my particular case, it was 13 hours, but once it's done, we have 500 billion rows inserted to a single machine at a rate of 1 million rows per second. This is not extremely fast, but good enough. So ClickHouse can actually do faster if you give it better hardware. And now let's look at our data. At the top, we can see how individual columns has been compressed. You see that sensor ID and time has been very aggressively compressed thanks to sorting and double delta. For temperature, it wasn't so good, but still we have at least 3 times compression. And overall, at a table level, this level of compression allowed us to feed our 6 terabytes of uncompressed data in only 700 gigabytes, slightly less of compressed data. So we feed the data in a single box. So the first part is done. What's next? Next, we can try to query the data. And surprisingly, if you query for a single sensor, then it's very fast. It's only 24 milliseconds to get some data for the sensor. We want to visualize it. I didn't have time to plug Grafana to that, but ClickHouse has internal visualization tool, which is called bar function, which can resemble you some old times, DOS times. And we can use it in order to visualize distribution for one particular day. So we have the data, we can query it. That's good. But what if we want to query for for all sensors, not just for one sensor, for the full data set? ClickHouse tries hard, and as you can see, it tries at a speed of 600 million rows per second, but still laws of physics exist, and this query will take several minutes or 10 minutes or 20 minutes. So we need to think of something else, how to do it more efficiently. And this is our rule number 3. We need to understand how to use the database in the most effective or efficient way. And for this scenario, what I tried to do is a materialized view with aggregation. Look here. So this is actually a complex construction which has both materialized view and materialized view in ClickHouse. It works as an insert trigger. In fact, I created this materialized view at the very beginning just to avoid the population, and it has been automatically populated once I inserted the data into the main table with raw data. And the logic of aggregating merge tree, which is again uniquely ClickHouse feature, is to aggregate data using certain rules. In this case, I want only to aggregate min and max, and there is a special functional data type in ClickHouse which is called simple aggregate function, which does the job. I could actually calculate average almost the same way, or on any other aggregate function that exists in ClickHouse, and ClickHouse has got quite a lot of them. So what it does for us is data reduction. If we look into row counts and size statistics one more time, we can see that we have 1,000 times row count reduction when we move to materialized view, and 300 times storage size reduction. Why? Because we actually calculated, aggregated by days, and this is sufficient for the use case and that ScyllaDB suggested. And here it is. So what we want to do, we want to find a sensor which is anomaly, which shows some anomaly. Anomaly means the temperature is very low, and this is not my definition. This is how those guys did. So in fact, I would probably use some different algorithm, looking at neighbors or using some probabilistic methods. But this is exactly the query that was used in StillDB article, and I used exactly the same. So in 2 seconds and for 2 and 4 seconds, we've got an answer which sensor is an outlier, and that's almost it. We can query it, checking that this is in fact defected sensor. We can see the drop in the distribution for this particular time and day. Problem solved. Since we have all the data now aggregated, we can also quickly generate data to be used in maps or in map applications. And this is just 5 rows, but the query for all million sensors, for all 1 million sensors, would probably take almost the same time. So in 3 seconds, we could generate data and to be used for the map like this one. I didn't draw this map, I found it on the internet, but if you use some map tools like Tableau or Carto, you can display the data efficiently from our 500 billion rows data sets. So what is the result of this exercise? And it's very simple. So ClickHouse can handle 5 billion data set even on a mini PC, which is, I can say that it's a junk hardware. It's a good hardware, but it's very small compared to servers that we typically use. And the main technique in order to get a decent performance is I/O reduction. So we decreased I/O using smart codecs and encodings, and that allows us to store data in most efficient way. And second, when instead of doing brute force search for raw data, we pre-built an aggregation that helps us to detect anomaly. We still can go to detailed data anytime when we need, but for analysis like anomaly detection or some mapping and stuff, we don't need the detailed data with mean granularity. It's sufficient to have the daily aggregate. And this is just a little piece of what ClickHouse can do. And it's not necessary only about 500 billion rows data set. ClickHouse can work on small data sets or any data set of your choice or desire. That's all. Any questions?
Hi, Alexander. Thank you for that. That was a great talk. Some questions are coming in right now. Let's see. Aren't you cheating aggregating the data? Is this a fair approach?
Yes, certainly it's a fair approach because you need to be smart about your data and about what you're doing. If you can do something more efficiently, then you have to do it. Sometimes you have to use brute force and you cannot aggregate. But if you can, this is a way to go. And ClickHouse is very good in aggregating and providing partial aggregates and things like that. In particular, ClickHouse has a unique feature of aggregating uniques. So typically you cannot aggregate unique. But since ClickHouse is built for cluster environment, and in cluster you always have to do some partial aggregations of unique, ClickHouse has a built-in feature to do that very efficiently.
Very good. Another question is, does ClickHouse work on Raspberry Pi?
Yes, you know, somebody tried to build it for Raspberry Pi. Unfortunately, I don't have a Raspberry Pi in my lab. Probably for the next talk, I will try something on Raspberry Pi as well. So ClickHouse can be built for ARM, and Raspberry Pi is not an exception. But probably you have to spend some time turning off some modern C++ functions that are used.
Very good. You showed a colored map. What map visualizations are available for ClickHouse?
So I mentioned that Tableau has a map tool or something like that, and Tableau works very well with ClickHouse over ODBC. Not very well, but reasonably well with ClickHouse over ODBC. And also I know that Carto, which is a company who develops map visualization software, they also use ClickHouse or have adapter for ClickHouse. Not sure about Grafana. If there is somebody who knows Grafana better than me, probably there's something for Grafana that can be used as well.
Let's see here. You mentioned linear regression. Can you tell more how it can be done with ClickHouse?
Yeah, this is, so if you want to do anomaly detection, so ClickHouse has several tools to do that. Probably the easiest thing is just to check the neighbors and see if the value is outside of neighbors, and or if there is a significant drop in measurement. And also ClickHouse has several built-in machine learning features, including linear regression. So you can build a regression model on your data and then compare particular value against the model. So, and if there's outlier, you will immediately see that it doesn't fit the model.
And finally, are you Peter's missing brother?
I'm not.
Okay, very good. Okay, well, thank you very much for your time, Alexander. We really appreciate it. I'll turn this over temporarily to Bronwyn now.
Thank you. Have a good rest of the day. Bye-bye.